All right, folks, we are back at it today. We are going to be starting chapter 7 with 7-1, which is basic trigonometric identities. So let's head over to the notebook and get started right away. There's a decent amount of writing in this. What we're going to do is start out with our basic trig identities and all the ways we've thought of them so far, just to kind of do a summary. Remember, we have our sine theta. And sine theta, in our most basic sense, we think of that as y over r. If you're thinking of x, y's, and r's, you can also think of that as opposite over hypotenuse. And we can also think of that as 1 over cosecant. Now, again, I bring this up because I want you to understand this connection between sine and cosecant that you're going to see when we do cosecant as well. If I go over here and look at cosecant theta, and that should have been a theta, sorry. For cosecant theta, we can say that's r over y, and we can also call that hypotenuse over the opposite side. And we can think of that as 1 over sine theta. These are inverse quantities. So all of these are going to come into play at different times. We've used the first two a couple times already. These last ones are the ones we're going to key in on in this section. So with cosine theta, again, we thought of that as x over r, or you could say adjacent over hypotenuse. And most notably for this section, we're going to think of that as 1 over secant theta. All right, and again, these are, underline these just so they stand out a little bit more. For secant theta, with secant theta, again, we would look at the reciprocal quantities, and we would have opposite over hypotenuse, and also thinking of this as 1 over cosine theta. And finishing out our big six trig identities, you've got tangent theta. And that, of course, is y over x, or opposite over adjacent, or for us, 1 over cotangent theta. I want to add that to our vocabulary in terms of tangent theta. So now cotangent theta. Cotangent theta as well is going to be x over y, or adjacent over opposite, and most importantly, 1 over tangent theta. These identities, these ones that you see as the reciprocal identity, where sine is 1 over cosecant or cosecant is 1 over sine, that idea is going to be something we use quite a bit in this section. So I want you to be aware of those. Now, we also have some others that I didn't write, just a couple others that I want to add in here, is that you can also say, remember that tangent theta is equal to sine theta over cosine theta. You can say that cotangent theta is equal to cosine theta over sine theta. So just another version of each of these. And you can, again, take different, I want you to know that there are different ways of looking at this. Because, for example, with this one, we could say that sine theta is equal to, by multiplying both sides by cosine theta, we could say it's equal to cosine theta tangent theta, right? That's another way of saying sine theta using this. Or you could say cosine theta is sine theta over tangent theta, right? That's using the idea that we can switch these two. So sine theta over tangent theta. And in the same way, we could say here that if I multiply both sides by sine theta here, I would get cosine theta equal to, what would it be, sine theta cotangent theta. All right, and we could also say cosine theta is equal to, or I should say sine theta, I'm sorry. Say sine theta by switching these two. Sine theta is equal to cosine theta over cotangent theta. And this is kind of leading you into where we're going with this section. The section is we're gonna have to be kind of flexible, and you have to have these identities known. We would strongly suggest you memorize them, whether you make flashcards for these identities, things of that sort, where one of the flashcards would be, say, tangent theta, and on the back you'd have sine theta, cosine theta. Or you'd have cosine theta, and on the back you have 1 over secant theta. So you could work from one end to the other. So you could make flashcards for these, anything you want to do. By the time we get done with this chapter, we will have somewhere in the neighborhood, if I remember off the top of my head, somewhere around 30 some identities, 32, I think this is the number that comes to mind. So we've got these identities. We're going to show you how to use them in just a minute. We're going to get into the uses. First, I just wanted to go through the identities themselves. We've got a couple others. When you think of our unit circle, and I'm just going to do a bad sketch, we have our X, Y, and our R, right? And we know that our radius in the unit circle, this is equal to 1. So what that's saying is in the unit circle, x squared plus y squared equals 1, right? If we have this relationship, then we know that x squared, if this is a right triangle, that x squared plus y squared will equal 1 in the unit circle, right? So if that being the case, remember x in the unit circle is our cosine value. So we could say if this is our theta, that cosine squared theta, and this is the way we say cosine of theta squared. You don't put it out here because then you don't know whether you're squaring the theta or you're squaring the cosine of theta. This means the cosine of theta squared. All right, that plus y is of course our sine, so sine squared theta equals 1. Again, I want you to understand that cosine squared theta means cosine of theta, that quantity, squared. Same with sine squared theta. That's our notation we use in case you haven't seen that before. All right, so what is this thing? Well, this is what we call Pythagorean identity. And there's actually more than one version of this, but this is the main one that they all come from. The rest are, as you saw on our last page, different variations on it. Pythagorean identity is that one that says cosine squared theta plus sine squared theta equals 1. But again, we can do some different things here to move this around. If I subtract sine squared from each side, right, we have this original, I'm going to box this in just so you can see, this is our Pythagorean identity. Now, if I subtract sine squared from each side, I get cosine squared theta equals 1 minus sine squared theta. This is another version of the Pythagorean identity. In the same way, if I started here and subtracted cosine squared from each side, I would have sine squared theta equals 1 minus cosine squared theta. Another version of our Pythagorean identity. You want to know all of these. All right, so we've got those. Now, what about, this is still under the heading of Pythagorean identity. What if I took cosine squared theta plus sine squared theta equals 1, and this is an equation, so with any equation I could divide by whatever I want as long as I divide everything, and it'll stay the same equation. So I'm going to divide everything by cosine squared theta. So here we get 1 plus, what is sine squared over cosine squared? Well, that's sine theta over cosine theta times sine theta over cosine theta. So that's tangent theta times tangent theta, or tangent squared theta. And what is 1 over cosine squared? Well, what is 1 over cosine? 1 over cosine is secant. So 1 over cosine squared is secant squared theta. This is another one of our Pythagorean identities, just another form. Now, if you can imagine, if we can do that by dividing by cosine squared, well, now let's look at that. We can also do that same thing where I take cosine squared theta plus sine squared theta equals 1, and I divide everything by sine squared theta. And when I do that, again, simplifying this now, cosine squared over sine, well, cosine over sine is cotangent, so this would be cotangent squared theta, plus if I have sine squared over sine squared, that's just 1, and 1 over sine squared, remember 1 over sine is cosecant, so 1 over sine squared is cosecant squared. And we have another Pythagorean identity. Now, this is where it gets really interesting because let's go back to this one. If I can do 1 plus tangent squared is secant squared, doesn't that also mean that secant squared theta minus tangent squared theta is equal to 1, just subtracting tangent squared from each side? Let me erase that. It's a little too close. All right, so we have that. That's another version. And if we can do that, we could also subtract 1 and say tangent squared theta is equal to secant squared theta minus 1. And again, you get the idea. We can start to move these all around. So what can we do with this one? Well, subtract 1, I get cotangent squared theta equals cosecant squared theta minus 1. Whoops, minus. Let's erase that quickly. Minus 1. And what else could we do? Well, we can do subtract cotangent squared from each side, and I would get cosecant squared theta is equal to, let's see if we're subtracting, no, I'm sorry, we were going to subtract cotangent squared from each side, so we can say that. Cosecant squared minus cotangent squared theta will equal 1. And we've got another version. So you've got really 9 different Pythagorean identities that all just come from this one main idea right here. And that is from that unit circle where x squared plus y squared equals r squared, and r is 1. So cosine squared plus sine squared equals 1 in the unit circle. So we have these to work with. Now we're going to get into what are we going to do with these? How are we going to use them? Well, we can use them in some basic ways, like just finding values for trig functions. For example, let's see. I need a new page, sorry. This is an example of how we could use these. And let's get, here we go. If cosine theta equals 1/4, find tangent theta. Well, what do we know that relates cosine and tangent? Well, we have the idea that tangent theta is y over x, yes? And cosine theta we know is x over r. So there's a couple ways you could do this. If you wanted to use your identities, we know there's a relationship between tangent and secant, right? Or if we go back here, we had 1 plus tangent squared equals secant squared, yes? And this is what they really want you to do. There's a couple ways of doing this. Oh, I went the wrong way, sorry. We know that 1 plus tangent squared theta equals secant squared theta. And if cosine theta equals 1/4, then secant theta has to equal 4, doesn't it? Because these are reciprocal quantities. So right now we could say 1 plus tangent squared theta equals 4 squared, because secant is 4. So 1 plus tangent squared theta equals 16, which means tangent squared theta equals 15, and tangent theta would equal, let's see what it would be, plus or minus root 15. Now they may tell us, if they say something like this is between 0 and 90 degrees, or first quadrant, then you'd know it's positive. If they say it's between 90 and 180, or second quadrant, or something of that sort, then we could say it's negative. Right now, with this information, we'd have to say it's either one of these, right? Because it didn't give us a limitation. Now, that's one way of doing this. You could have also said, since I know cosine theta equals 1/4, that's x over r. And I could have said then that I know x squared plus y squared equals r squared. And I could have said 1 squared plus y squared equals 4 squared. So y squared equals 15 again, and that makes y equal to the plus or minus root 15. So then we could then do a tangent theta, we know is y over x, which for us then would be plus or minus root 15 over x of 1. So that would be plus or minus root 15. All right. Both of these work, and it's just being flexible with those identities as to which one you see. All right. So let's do one more of those. Let's do, let's see. If tangent theta equals 7 over 2, find sine theta if theta, well, let's do it this way. Let's put theta there, and we'll say up to 90 degrees. So now it's telling us theta is between 0 and 90 degrees. They told us tangent theta equals 7/2. They want sine theta. How can we relate sine theta to tangent theta? Well, there's a couple different ways we could go about it. If you want to, again, think of tangent theta relating to secant theta, we'd have to have cosine, right? But we do know that cotangent theta relates to cosecant in the same way. Again, you're going to have to get used to these. Right now, I'm going to go back to show you. We have cotangent squared plus 1 equals cosecant squared, right? Or 1 plus cotangent squared equals cosecant squared. So if we know that 1 plus cotangent squared theta equals cosecant squared theta, well, if tangent theta is this, we know cotangent theta is 2 over 7, right? And if using that, we can find cosecant, and if we have cosecant, we can find sine because we want over it. A little bit of a trail to follow there, but we can do it. So we'd have 1 plus 2/7, that quantity squared, equals cosecant squared theta. So that's 1 plus 4/49 equals cosecant squared theta. And 1, in this case, I'm going to think of this as 49 over 49 instead of 1. So 49/49 plus 4/49 make 53/49. And that's going to be equal to cosecant squared theta. That makes cosecant equal to, we got to take the square root of both sides. Square root of 53, nothing I can do with that. And then that's over 7. So if this is cosecant, remember they wanted us to find sine. Well, that would imply that sine theta, remember, sine theta equals 1 over cosecant theta. So that means 1 over this or the reverse. So that means sine theta equals 1 over root 53 over 7, which equals 7 over root 53, which we cannot leave that way. We got to multiply top and bottom by root 53 to rationalize that denominator so that we get 7 root 53 over 53. And we've got our solution. Now, could we have done that with x's, y's, and r's? Absolutely. Your tangent is y over x, so we already knew right then that y equals 7 and x equals 2, right? And we're looking for sine theta. We know sine theta is y over r, so we need r. And we know that 7 squared plus 2 squared equals r squared. So 49 and 4 is 53 equals r squared. That makes root 53, again, because we're in first quadrant. The positive root 53 is what I meant to say there, as our r value. So our sine would equal y over r, which is 7 over root 53, which is 7 root 53 over 53. Same thing we got the other way. So there are options here. These generally people don't have big problem with. What I want to get into is another thing that is, as I've mentioned before, one of the major goals of this year is you need to know how to simplify different quantities when they are written out in a way you're not used to. All right, so if I say simplify and I give you something like this, cosecant x minus cosine x cotangent x. And you say, well, what do I do to simplify this? Well, what we're going to try to do is get this. There's some different strategies. One thing is to rewrite things in terms of sines and cosines. Another is to try to get, if you have more than one term, get it into a single term. What we're trying to do is make this into a simpler form so we can use it easier. Right now, it's kind of a long quantity. And what I mean by that is I can look at cosecant x and think of that as 1 over sine x, right? Using those identities from the first page. Cosine x is just cosine x. But since I'm making a fraction there, I'm going to make that a fraction here. And that times cotangent x. Well, cotangent x we know is cosine x over sine x, right? So again, using our identities. And these are ones you got to know as quickly as you just saw me kind of go to that. You're going to have to know these by heart. So now, what do we have here? We've got 1 over sine x. By the way, you are going to want to, this is kind of like a proof. You're going to want to be very picky about showing each step so we can follow along. Because if we can't understand where you got something, if you haven't neatly shown it, then we can't give you credit for it. All right. Now, on the good side of these is as you do a productive step, you get points for it. Every productive step. So you want to do as much as you can, go as deep into these as you can, and try to get it as fully simplified as possible. All right, so now I've got this. This is a little easier to look at than what we started with, but one thing I notice here, again, remember I said if we have more than one term, we often like to get it as a single term. Well, we've got a common denominator. Well, with a common denominator, I can write this as 1 minus cosine squared x over sine x, right? And remember, does this look familiar? It will real soon. It's going to be like a screaming neon sign to you once you get used to these identities. 1 minus cosine squared or 1 minus sine squared are big ones. And again, I go back to those Pythagorean identities. I want you to see it again in case so you don't have to rewind. We had that Pythagorean identity, but we also had this one. Cosine squared is 1 minus sine squared. Sine squared is 1 minus cosine squared. That's what we got right there. So we have a sine squared there. All right, so let's go forward. So like I said, 1 minus cosine squared. This is sine squared. So we have sine squared x over sine x. Well, what does that mean? If I have anything squared over itself, doesn't that just one of them cancel? And I'm going to write this out this time. I wouldn't write this out in the future, but I'm writing this out for those that may not see what I'm doing. This is what we have right now, right? So I can cancel one of these, and that'll just leave me sine x. And that's as simple as it gets. It's a single term. It's not fractional. That's the best we could hope for. We took this thing, which, by the way, once you get to calculus, this is very hard to take a derivative or an integral of. This is something that you pretty much have memorized. It's immediate. So what could take you lines and lines of work has now become something that you can do very easily. And that's the point of this simplification process, is to give us a simpler version. This whole thing here is equivalent to sine x. I know it seems crazy, but that's what it is. And so that's what we go with. All right, let me find another one to do. So we could do something like this. Again, we're just simplifying. And with simplifying, we have, say, cotangent A over tangent A. All right, so what can we do here? Well, cotangent is cosine A over sine A. And make sure you're writing. I have people that'll shorthand and not put the A's or the thetas in here. Don't do that. Make sure that you're writing a complete, again, this is like a proof. So good notation, solid, clean. I also recommend going up and down when you're doing this. Start at the top and work in columns. Working in rows becomes very problematic. I've seen more people make mistakes working in rows than working in columns. It's easy enough if we get one column done to create another column. All right, so what is that? Well, it's a fraction over a fraction. So I'm going to take the top fraction and multiply it by this flipped, right? It's times cosine A over sine A. And the one thing I do need to mention right here, guys, is that you may see something different than your neighbor. I'm going to show you two ways of doing this particular problem. And I'll show you what I mean by that. So you and someone else could do it completely different and both be right. So this is cosine squared A over sine squared A when I multiply straight across, right? That's what we do with fractions. And what does that mean? Well, cosine A over sine A is cotangent A. So this would be nothing more than cotangent squared A. Again, much easier to look at than cotangent over tangent. All right, so cotangent squared A. Now, how else could we have done that? Well, right off the bat, what do we know about cotangent? If I have the same thing again, let's do it the same problem again. Cotangent A over tangent A. Well, cotangent is 1 over tangent. So it's 1 over tangent A, right? Then over tangent A. So if I write this out as multiplication, 1 over tangent A, that's the top one, times this one we think of as tangent A over 1, but when we divide, we have to flip it. So we would do this, and we would get 1 over tangent squared A. Now, again, you may need to stop, rewind, or in this area, because I'm going kind of fast because I want to give you as many examples as I can in as short as time as I can. But again, looking at this, 1 over tangent squared, immediately in my head, I see that as cotangent squared A, because 1 over tangent A is cotangent A. So 1 over tangent squared is cotangent squared. So I get that same answer in a completely different way. And this is going to be something that is going to frustrate some of you because you want that one way of doing this. And this whole chapter is going to be multiple ways of doing the same problem. So it's going to be up to you to make sure you're flexible and make sure that you understand these. And first and foremost, you got to understand and have memorized those identities. If you don't, and you just keep referring to your notes, you're going to get to the quiz or the test and it's going to fall apart because you'll just burn time. You won't know what to do. You won't get to practice. If you practice these consistently, what you're going to find is they kind of start to look alike. They start falling into different patterns that you're used to. All right, one last one. Again, if you're feeling comfortable, go on ahead. I'm just going to do another simplify for those that might want to see a hard one. All right, and let's do this one. Tangent x minus sine x cosine x all over sine squared x. So let's see, what do I want to do here? Well, let's do this. Let's just write this in terms of sine and cosine. What you're going to find is once you do have these things in your head, you're going to start to like overanalyze some things. And you're going to see 5 different things you could do. Just do one of them. Don't sit and stare at these problems for long. Like I kind of looked at that for about 5 seconds and I thought, you know what, I've got too many ideas. Just use one of them. So this is one of them that I'm doing. All right, now I see 2 things together up here. I'd rather get that into a single term. So I'm going to get a common denominator here. This has a denominator of cosine. This has a denominator of 1. So I'm going to do cosine x over cosine x and make this equal to, this side is still going to be sine x over cosine x. But now it's going to be equal to sine x cosine squared x, right? When I multiply this by that, over cosine x. And then it's all still over sine squared x. Again, you need to write these out completely, guys. Every year I have people that get angry at me when I mark things wrong, when they don't write out all the steps neatly and clearly and show me what the next step is. So common denominator, sine x minus sine x cosine squared x all over sine squared x gives me, let's see, oh, I'm sorry. It's over cosine x. That whole thing over cosine x is then over sine squared x. All right, so what does that give me? Well, it gives me the option of multiplying by thinking of this bottom one as sine squared over 1. And again, this is not the only way, guys. There's a few different ways you could approach this. I am just showing you one of those ways. So I can write this now as multiplication. And that would mean I have sine x minus sine x cosine squared x all over sine squared x cosine x. All right. I think what I'm going to have to do is I'm going to factor out a sine x on top of this part. And that would make 1 minus cosine squared x, right? Factoring a sine x out of this. And then I'll have sine squared x cosine x. So what does that do? Well, what is this? That's sine x times sine squared x over sine squared x times cosine x. Those cancel, leaving me sine x over cosine x. And what is sine x over cosine x? Well, it's tangent x. Kind of took a long way there. Again, I just followed the path. There's probably a quicker way. But again, multiple ways of getting these answers, but you want to get to where it's done. And the question always comes up. How do I know I'm fully simplified? You can't do anything else. That's what it comes down to. So you want to always try to get it down to as few terms as possible. Try to get to one term if you can. Sometimes you can't. Sometimes you'll end up with two terms being added or something of that sort. But you want to get it as simplified as is possible. All right. And that's what we're doing, guys. We're doing those types of problems with these identities. So it does take some work. You have to know these identities. If you're not a flashcard person, personally, the way I do it is I look at my notes, like what the ones I just gave you. I try to memorize them as I go. Then I put away that note thing and I write down. I just try to write every identity I can. If I can write those first 6 identities in all their different forms, and I can write the Pythagorean identities in their 9 forms, I know I'm done. And sometimes I can only get 6 of them. If you first start, you can get 6. You stop, look at which ones you didn't get. Now try again. Start from scratch. Write all nine of the Pythagorean identities, all 6 of the original identities. All that stuff. If you keep writing it, usually with me, it takes about 4 or 5 times of trying to make a list until I get the full list. And what I like about writing it is the same thing many people say about flashcards. They get a visual image in their head of that identity, which is really helpful when you're doing these simplified problems because you get to see the 1 minus cosine squared is sine squared. They start to jump out at you once you see them visually. So that visual part of this is kind of important in the big picture. All right, so that's what we're doing, guys. Don't give up on these. Don't look at the answers until you've given them a really good, at least a couple times effort through. Then maybe look at how the book did it. Don't do it before that. All right. Good luck, and we will help you in class, guys.